Okay, so like I said, we're going to start nonlinear vibrations for multi-degree of freedom systems here. We're going to go through an introduction. We're then going to talk about linear normal modes briefly as a recap, and if you need a deeper explanation of them, I can give you some videos for that. We'll then see how incorporating nonlinearity leads to modal coupling, and then we will study internal resonances for modal coupling. All right, so in contrast to single degree of freedom systems, which will only have a single linearized natural frequency, and you could say a single mode of motion, an n degree of freedom system that has n linearized natural frequencies and n corresponding will have n corresponding mode shapes. So a linear system, the number of natural frequencies is equivalent to the number of degrees of freedom. As we go through this chapter and in the next chapter, we will go through and actually show this. There are cases where you can have multiple, for a single frequency or a single modal assumption, you can end up with multiple modes. And so the number of modes is not equal to the number of degrees of freedom. We'll show that when we go to the next chapter explicitly. All right, so in this case, we're going to denote these linearized frequencies as omega 1, ... all the way up to omega n, and we're going to say that they are not equal to 0, so we have no rigid body motion is what we're assuming here. And then we're also assuming that the modes are distinct, meaning that omega 1 is our lowest frequency, and then omega 2 is greater than that, and so on up to omega n. And so none of the natural frequencies here are equal to each other. That's what we're assuming here. In cases where they would be equal to each other, you can show cases of like a one-to-one resonance between modes. We're going to not do that, but you could show things like that. All right, so again, this is a nonlinear dynamics class, nonlinear vibrations class, so we're interested in when nonlinear behavior can occur. And really the most interesting time is when one of these, two or more of these linearized natural frequencies are commensurable or nearly commensurable. And by that we're meaning things like omega 2 is approximately equal to omega 1, to omega 1, twice omega 1, or omega 2 is approximately equal to 3 times omega 1, or you can have combination resonances where, for example, omega 3 is approximately equal to omega 2 plus or minus omega 1, or omega 3 is approximately equal to 2 omega 2 plus or minus omega 1, or you could even take it a step further and say that omega 4 being approximately equal to omega 3 plus or minus omega 2 plus or minus omega 1, and so on. You can continue to construct these types of combinations. The key thing is that they should be related by an integer ratio approximately. And certainly when you do experimental measurements, and when we will study this for measurements like these resonance conditions, you'll find that the ratio will not exactly be like 2 to 1. It will be like 2.05 to 1, close to 2 to 1. Okay, and when we go through the forced response, we'll introduce the detuning parameters, which will show how they'll be approximately these ratios. All right, so the type of like resonances or internal resonances that can occur, basically, you know, whether or not this relationship causes a resonance or this one causes a resonance, that depends on the type of nonlinearity that is in the system. So specifically, again, this coupling is called internal resonances. So it's where energy can be exchanged between between two or more modes, we'll say. And it can go from low to high frequencies or from high to low frequencies as well. Yep. Yeah, okay, so when this happens, like I said, there's these energy exchanges, and you end up having to study the oscillations of the system on some higher dimensional manifold. We will see a little bit of this later when we look at nonlinear normal modes. We'll specifically start with the Shaw and Pierre. We won't start with that, but one of the types of nonlinear normal modes we'll study is Shaw and Pierre's definitions for them, which shows how each nonlinear normal mode is in itself lives on a manifold. And then when you have these internal resonances, those manifolds stop being in like a two-dimensional manifold, they end up becoming three or four-dimensional manifolds. Okay, so like I said, it depends on the type of nonlinearity. And so for example, if you have a quadratic type of nonlinearity, you can get internal resonances when one mode has twice the natural frequency of another mode, or when they're equal to some types of combinations of them. For cubic nonlinearities, you will get internal resonances when they're related by a ratio of 3 to 1 or 1 to 3, or the natural frequency of one mode is equal to 2 times that of another mode plus or minus a third mode. Or maybe a fourth mode is equal to the summation of another 3 modes' natural frequencies. We are only going to consider cubic nonlinearities simply just due to time constraints. There's a number of interesting phenomena that arises in quadratic nonlinearities, particularly saturation phenomena, which we won't see in cubic nonlinearities. I think we're going to see that a little bit on the next page, though. Let's see. Maybe not. But basically, saturation occurs when you're forcing a particular mode directly, and that mode reaches a maximum amplitude it can achieve, and then starts to pump energy into another mode instead, even though you're forcing directly only one mode, and it may not be in one of these internal resonances. We won't find that in a cubic nonlinear system, though. All right, let's see. Okay, so when you have an internal resonance, it's like opening a window between two modes, and it allows them to suddenly interact and talk to each other. So if you just think about a linear system with linear normal modes, they are totally orthogonal and independent of each other. They can never exchange energy in any kind of way. And as a result, if you give one mode energy, it can never share that energy with any other mode throughout the entire response, whether that's steady state or transient response. These internal resonances open up a window that then allows them to interact and exchange energy. And depending on the system and how it evolves, these could be continuously interactions for all time. They could continuously exchange energy. It could be a transient phenomena where it rises at a particular time and then ends at another time. It all depends on what the system has, particularly for example, in free response or free vibration response, you can have transient resonant captures or transient interactions between modes where they will briefly interact and exchange energy and then stop interacting with each other. If they're being forced, you can force them in a way that they'll continuously exchange energy for all time. Okay. What else? Right, so in addition to these internal resonances that occur between these two modes, when we start to add forcing in, then in addition to what we saw, these primary resonances, these secondary resonances, we can get these resonant combinations of frequencies, which can take the form of something like P times capital omega is equal to A1 times omega 1 plus all the way up to A, we'll say AN times, we'll use a capital N, AN times omega N. And here P and AI belong to the set of natural numbers, so your typical counting numbers or integers, not including 0. And this is then true for I equals 1, 2, all the way up to N, where N is, in this case, the number of modes that are acting in this resonant combination of frequencies. And in this case, we can also then say, let me first move this equation down a little bit. We can say that P plus the summation from n equals 1, lowercase n equals 1 to big N times the absolute value of A and must be equal to M, where M here is the order of the nonlinearities, so 3 if it's cubic, plus 1, so it would be 4 if it was cubic. And N again is the number of degrees of freedom. All right, so this next bullet is about the saturation phenomena that I talked about. If you study a quadratic system, you can prove this saturation phenomenon appears. We're not going to see that in the notes here. We might do that in a homework assignment instead, but the techniques will be the same as what we'll do in class, just applied to a different system. Okay, yeah, and so it's also possible for no steady state motion to exist. Despite damping, you can have no steady state motion, you can get quasi-periodic motions, you can get totally non-regular or aperiodic motions, and generally in cases like this, you can have energy being continuously exchanged between two or more modes. All right, we're going to just take a look at an example of a nonlinear multi-degree of freedom system. In this case, we're going to consider a spring pendulum. It's just your basic pendulum, but instead of having a wire or a rod, we now have a spring there. And we're going to consider it with a mass of m. And we're assuming that it swings only in the vertical plane, so it's constrained to swing in that plane. Unstretched length of L for the spring, and spring has a stiffness of K. We're going to just jump right to the governing equation, which is x double dot plus omega 2 squared times x minus L plus x times theta dot squared minus g times the cosine of theta, and that's all equal to 0. So x is the stretch in the length of that spring. Theta then is the angular displacement of the pendulum. For theta, we're going to get theta double dot plus the quantity. It's going to be a big fraction, sine, g times sine of theta, plus 2x dot times theta dot divided by L plus x, and that is all equal to 0. And here omega 2 is equal to the square root of k over m. So it's like the linearized natural frequency for the spring portion, or the translational displacement. Okay, if we go ahead and neglect nonlinear terms, and what we're going to end up with is two uncoupled single degree of freedom linear oscillators. The first equation is x double dot plus omega 2 squared times x equal to 0. And the second equation is theta double dot plus omega 1 squared times theta is equal to 0. And here omega 1 is equal to the square root of g over L. So we can see here that once you get rid of that nonlinearity, there's no coupling in these equations. And then based on linear theory, you would expect there to be two uncoupled modes, one just a spring mode that just bounces up and down, and then a second one is just a pendulum mode with a frequency omega 1. So just to be clear, what I'm saying is that based on linear theory, when we study equations 3a and 3b, we would expect there to be two modes that are uncoupled, each with separate frequencies. However, when... Yeah, go ahead.
So for the first equation,
yeah,
what we did is almost linearizing things here.
Yep, that's exactly what we
For the
did.
first equation, why didn't we keep the minus g?
We should have kept the minus g. And put it over here. You're right. Oh, whoops. That should have remained because it's still subjected to gravity. I mean, it should fall due to gravity, right? Yeah. Okay, so it turns out when omega 2 is approximately equal to omega 1, the two modes become nonlinearly coupled and energy will get continuously exchanged between them due to an internal resonance. And this gives rise to what we call a nonlinear beat phenomena. And so what I've done here is I've just done some numerical simulations for equations 3a and 3b. In this case, I've used the linear omega 1 squared just to determine parameters. It's very simple. I've just set, we'll go down to the code and take a look right here. So simply I've just set g equal to 1, L equal to 1, and then omega 2 equal to 2. Yep, so we can just directly get this 2 to 1 relationship. Okay, so, and then we're going to vary initial conditions. Actually, let me go back up here. So here we're just varying initial conditions. We're starting in the first plot. We have a large value for x of 0. It's actually twice the equilibrium position. And then we have a very, very small starting initial position for theta, so a very small initial angular displacement. And what we end up with on the right is just a zoomed in view on a short time scale. You get this singular beat that appears right here, which corresponds to a beat appearing in the theta equation right there. This is what we call this nonlinear beat phenomena, because this is a beat. This right here is a beat. And then you can see that we have this kind of slowly varying amplitude as well that we've been talking about throughout this. If we go to a longer time, up to a time of 1,000, you'll see that this beat is periodic and it repeats every so often. At this energy level, it's periodic, and again, it's this continuous exchange of energy. And so in this case, we're looking at exactly 2 times omega 1 for that ratio. It's exactly 2 to 1. If we go to 2.1 to 1, in this case, you'll see we still get this beating phenomena, and this is what I'm saying. It doesn't have to be exactly 2. It's just going to be close to 2 or close to 3 for another system, for example. And so what we're really looking for is this kind of beating phenomena that appears. And when we look at like signal processing, and we'll see in wavelet transforms how you can find this kind of behavior in these kinds of signals. Again, in this case, it's so periodic, it's the same initial conditions. Here we're looking at now 1.9 times omega 1. And again, we're still getting this nice periodic beat appearing that it shows up. If we go all the way up to 3 times omega 1, which is now far away from that ratio of 2 to 1, we no longer have this beat phenomena that shows up. There is a little bit of a slowly varying amplitude over here, but it is not an exchange of energy between the two. So again, this is a 2 to 1 relationship that occurs. All right, if we go back up to 2, and we now just change a little bit the initial conditions. In this case, actually, let me just check, where are we at? So in this case, actually, this value right here, right here, this is actually the equilibrium point for this system. So this is essentially saying x is now starting at 0 for this initial condition. It's its equilibrium point, but we're providing a very relatively small initial angular velocity here, and you can see how the translational displacement now exhibits this beating phenomena in the sense that its amplitude starts small, grows, decreases, and then repeats this process. In this case, this is a periodic response still. We're still at a low enough energy to get that. If we take a look at theta, it's hard to see here. I'm going to zoom in here. There is a beat phenomena that occurs right here, but it's harder to see here simply because at this energy level, there is not a lot of transfer into that translational mode. Okay. Any questions? Mohammed, you...
Actually, I did my research. So this pendulum, when you displace it, give it the initial condition, so at some point it starts to, even you didn't give this, angular position, but it starts to do it, right? So the energy exchange between the two modes. So I did my research actually on this one, and you're exactly doing it at the 2 times of the omega, which they call it the parametric resonance, right?
Yeah.
So about that question that I asked this last time, I did my research and it's getting me more confusing. These things that you just said.
Yeah.
It's just like, you call it Betting phenomena, they call it parametric resonance, some of them call it autoresonance parameters. And it's a lot of.
Sure. Yeah. All right. So let's try and talk a little bit about terminology here. So parametric resonance occurs when. So if we think something like here, parametric resonance, if we go back to chapter 3 when we talked about forcing, is specifically, I'm going to try and find a little white spot. When you have something like s dot plus omega, and this frequency here is depending on time. This is a parametric resonance type of phenomena. And it can show up here as well. Now, beating phenomena is specifically talking about this type of profile where you get these series of beats, and they result from resonance. In fact, you can show that the beating phenomena is a violation of what the averaging theorem, which then ties it into a resonance phenomena. So in this case, you're right, this is a parametric resonance in this case, and it's causing the beat phenomena. As we continue and get out of this example, we will then see how you can, we'll see the exchanges. We'll see how you can get this beating phenomena and this type of exchange of energy without a parametric resonance. So parametric resonance, in summary, specifically talks about where the time, like a time-varying frequency is, rather than having like a nonlinear forcing term in that case. And then beating phenomena is simply just the appearance of beats. That's what this is called. Because it sounds like boof, 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 right?
And to the question that you asked me,
Yeah.
They are not related, but it seems that at some structures, when you start to excite the structure at nearly 2 of the fundamental, 2 times the fundamental frequency, the structure starts to change some of its parameters that excite also that parametric resonance. It's crazy. So.
Okay. Yeah, I heard that it's very common for like these self-excited oscillations to occur in like turbine blades, for example. I personally have not studied that. No. And I think, we'll leave it at that, I think. All right, any other questions? Okay. We're now going to apply a harmonic force to this system. In this case, we are going to consider the system. Let me change that. Consider x double dot plus omega 2 squared x minus the quantity L plus x times theta dot squared minus g times the cosine of theta is equal to F1 times the cosine of capital omega 1 times t. And then our second equation will have a theta double dot plus g times the sine theta plus 2 x dot theta dot over L plus x. And this is equal to F2 times the cosine of omega 2t. And here we're assuming that these forcing terms act however is necessary for them to end up in this form in the equations of motion. So if we're restricting F to just always be, in the theta direction, that's what we're requiring. And then F1 is always acting parallel to the spring direction, or parallel to x. Okay, so in this case, let's just come back down here real quick. So in this case, we've actually gone ahead and we've set omega 2 here to 4, and we've set big omega to 4, and big omega 1 to 1. Also, the parameters will be shown up here. Okay, let me go back up and just make sure that everyone was able to write these equations down.
Just to confirm, in the cosine term, that is a subscript 1 and not a comma, such that it's cosine of omega 1t, not
Yeah.
a function of omega n.
Yeah.
Okay.
Yep, that's a 1, that's a 1, and yeah. Okay, so first case we're going to look at here is when we're forcing theta at the natural frequency omega 1. Here, because I've increased omega 1 to 4 rather than 2, here, this is now our new equilibrium point for x. And in this case, we're not forcing x, we're only forcing theta, and yet we still see that there's this beating phenomena that occurs in the sense that x starts at equilibrium, increases, and then decreases. And in fact, this case, both theta and x are beating at the same rate, although they're not oscillating at the same frequency. So theta here is oscillating at a lower frequency. It's oscillating at its omega 1, which is equal to 1, and x is oscillating in this terms of these fast frequencies on the inside. X here is oscillating at 4, which is the forcing. So we're forcing theta, but still getting a strong response in x here. And again, we get these slow amplitudes like so. And if you expand it out to a longer time, you see that this repeats. Here it's nice and periodic. And it is, in terms for theta, it is symmetric. For x, it's actually not symmetric. Okay. And their beats do not line up exactly either. Okay, so here we are still forcing theta. I think here we've actually increased the amplitude of the forcing. So previously we were looking at 10 to the minus 3. Now we've increased that by a factor of 10, shown there, and we're still getting this beating phenomena, and the time scales have changed. We're going to continue to increase this and see what happens. And then suddenly what ends up happening is we go from having a nice periodic response to having something that is not perfectly periodic, and it's likely quasi-periodic, meaning that we've now entered an energy level that's high enough to induce chaos into this system, meaning that this is a chaotic response now. Okay, and so the reason you can see that is not periodic is if you just look at like the peaks here, 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 and you just take a look at all those peaks, you'll see that they're not a repetitive pattern here. And the time step here is small enough that we would capture any kind of, it's not due to like a sampling error. Okay, and if we go up even higher in this forcing, in this case, we just get a totally non-regular, aperiodic response. And again, this is just due to the chaotic nature of the system at this energy level.
So quasi-periodic just means like some characteristics of the oscillation are periodic and some are not?
No. So quasi-periodic means that it's almost periodic, but it never, so like it almost comes back to where it started, but it never comes back exactly. And so, we're thinking about things in terms of a period here. So if we were to say that, if 50, let's just say 50 is the period of like the beat here, what's going to happen is that if you were to track the amplitude at every period 50, you would find that it varies a little bit.
Then we can see it.
Yeah.
Oh, okay.
Yeah, exactly.
just looking at it, it looks like the beat is always the same, it's just the
The ends?
higher frequency
Right.
instead of the beat is different, but you're saying everything about it is slightly different.
Right. I'm saying that the fact that it is not even, even though like the beat structure appears periodic in general, you could look at like the width here and you'd find that that varies as well. It's very, it appears like it's periodic, but if you actually check, you will find that it's not.
Yeah, if we look at the one, like the second one in the middle for theta, if
Yeah,
you just look
yeah.
at them, they look almost the same
Yep.
each time, but if you look at the details,
Yeah.
you can see they are not the same magnitude.
Yeah.
the same.
You can see the peak, this, singular peak. All right, let me clear that. Singular, like max peak there. Then there's like 2 over here, another 1. So again, first glance, these look periodic, but when you, like you said, when you really look at the details, that's when you can see. I'll zoom in to help with that. So we're looking at like here, you get this nice single peak. Here you kind of get 1. Here you get 2. Here you get another 1. And the thing is that here, like the order has reversed. This is in between, those 2 and so forth. You have another question?
Yeah, is it just coincidence that, can you go back over to the theta on the larger or smaller time scale?
Here?
Is it just coincidence that they're basically mirrored about like 110 seconds?
You're talking about mirrored this way?
So if you take a vertical cut and, yeah, so they're basically mirrored about that point. Is that just coincidence or?
It is, well,
So I think if you look at the one with the 1,000 seconds,
mm,
it's almost repeatable every 3 periods.
yeah. Yeah, you can do things like what are known as Poincaré maps and really study this in detail, and that's what we will do. There are ways to study this, there's questions of periodicity versus like quasi-periodicity and so forth. It could potentially be periodic on like an order 3 like that. I didn't do the Poincaré map, so I don't know, When you counter signals like this that, look periodic but don't look periodic, this, invites you to do a deeper study, I'll say. Now, certainly something like this response right here, when we've increased it to a force, or F2 now is equal to 1, here there's no periodicity at all, for sure. So, that's, here there's none. And generally you have like a transition from periodic to quasi-periodic to non-aperiodic, which is why I'm guessing that this is quasi-periodic. But I can't say for sure without having actually investigated. And so you should not, again, I say likely quasi-periodic, you should not claim things for definite that you can't back up, for sure. Okay, any other questions before we move on? Okay. All right, we're going to do a very brief review of linear normal modes. We're not going to go through and do like the full theory of how you derive linear normal modes. And if you want to see something like that, I have videos I can share. Okay, and again, we already saw this bullet point. If we have a system with n degrees of freedom, we're going to have n modes and n natural frequencies. We're again just going to denote these as omega 1 all the way up to omega n, and these are not equal to 0, so again, we're ignoring rigid motion here. And once again, we're going to say that they are distinct, and omega 1 is the smallest, then omega 2 is the next smallest, all the way up until we get to omega n, and so on, such that they're distinct. So here we're not considering continuous structures either, we're just considering discrete structures as well. Okay, all right, we're going to denote the mode shapes here as phi1 for the first mode shape, phi 2 for the second, so on all the way up to phi n. And we're going to assume that they are what's known as mass orthogonal, which means that if you do a multiplication of phi I transpose times the mass matrix M times phi j, what you're going to get back is 0. In this case, where here I, j are equal to 1, 2, all the way up to n, and I is not equal to j. So they're mass orthogonal, meaning that you have to have this mass matrix in there in order for them to equate to 0, and that means then that phi I transpose times phi j is not necessarily equal to 0 unless the mass matrix is an identity matrix. Then they are orthogonal with respect to each other. Unless the mass matrix is an identity matrix. Okay, so if they are also mass orthonormalized or mass normalized, then we can write that phi I transpose M times phi j. This is equal to delta ij, and here delta ij is equal to 1 when I is equal to j, and 0 when I is not equal to j, which tells us then that this delta ij is an identity matrix. Okay, so if the modes are mass normalized, then we can also define phi I transpose times k, which is our linear stiffness matrix. We can get from that phi I transpose times k times phi j is equal to omega I squared times delta ij. Again, where I, j are equal to 1, 2, all the way up to n. And so in this case, we will get a diagonal matrix where each entry along the diagonal is one of the natural frequencies squared. Okay, we're then going to form what's known as a modal matrix, which is effectively where you stack each of these mode shapes, which are just a vector, each of them into a column, and we'll call that the modal matrix capital Phi. And again, each column of phi, of capital Phi, represents a single mode, and then we can decompose the governing equation as follows. And just as a note, this governing equation is something like mx double dot, and we're going to ignore damping and just say kx equal to 0. So in this case, if we substitute in that x equals phi eta, where eta is a function of time here, what we'll end up with is, first off, mx double dot plus kx equals 0. This then becomes m times big phi times eta double dot plus k times big phi times eta equal to 0. We're then going to pre-multiply by big phi transpose, which we will then get phi transpose m phi times eta double dot plus phi transpose k phi times eta. That's equal to 0. This first expression here, this is just an identity matrix. And the second expression is a diagonal matrix with the natural frequency squared along the diagonal. And so what we end up then with is I times eta double dot plus that diagonal matrix with omega I squared along the diagonal times eta is equal to 0. And from there, we end up with a set of decoupled or uncoupled ordinary differential equations where we can say that eta I double dot plus omega I squared times eta I is equal to 0. So for each mode, we end up with a single second-order differential equation that governs its evolution over time, such that you can then solve each of these equations separately, find eta, plug that back in for our assumption at the top here, for x here, and then you can then find the response of the system. Here we've not looked at forcing, and we've not included damping. So long as you have proportional damping, you can then expand and incorporate it there. If you have non-proportional damping, then you've got to use complex modes, which we're not going to cover or go into. Okay, so any questions on linear normal mode theory in general? Okay. In that case, we are going to look at how linear normal modes fail to decouple equations and motions when nonlinearity is incorporated. And to do that, we are going to look at just a 2-degree of freedom system shown here with a single nonlinearity, this x cubed term right here. And I'm about to write out what the equations of motion are. We're going to look at this. We're going to use the underlying linear normal modes to try and decompose this, and then we'll see what ends up happening. So our first equation is x1 double dot plus 2x1 minus x2 plus x1 cubed. That's equal to 0. The second equation is x2 double dot plus 2x2 minus x1, and that is equal to 0. We're just going to write this out into matrix form. In this case, our mass matrix is 1, 0, 0, 1. So here we do have an identity mass matrix. This is multiplied by the vector x1 double dot and x2 double dot plus 2 minus 1, 2. That's our linear stiffness matrix multiplied by the vector x1, x2 plus our nonlinear forcing vector x1 cubed and then 0, and that's equal to the vector 0. That first matrix is our mass matrix. Second one is our stiffness matrix that we typically look at. Okay, so if we ignore the nonlinearity for right now and just consider the underlying linear system, if we go ahead and compute the underlying linear normal modes, what we'll find is that phi1 is equal to 1 over square root 2 times the row vector 1, 1. So this is in phase motion, each oscillator moving together in the same direction at the same time. The second mode, phi2, is equal to 1 over the square root of 2 times the vector 1 minus 1, and then this is your typical out of phase mode. Okay, so then our modal expansion, which again is that x is equal to phi times eta. This is equal to the vector x1, x2 is equal to 1 over the square root of 2 times the matrix 1, 1, 1 minus 1 times the vector eta 1 and the vector eta 2. Okay, we're now going to substitute that into our matrix form of the equations and pre-multiply by big phi transpose. This ends up giving us 1/2 times the matrix 1, 1, 1 minus 1 times mass matrix 1, 0, 1, or 1, 0, 0, 1 times the modal matrix 1, 1, 1 minus 1 times the modal acceleration vector eta 1 double dot times eta 2 double dot plus 1/2 times 1, 1, 1, 1 minus 1 times our stiffness matrix, which is now 2 minus 1 minus 1, 2 times, again, the modal matrix 1, 1, 1 minus 1 multiplied by our modal vector eta 1 and eta 2. I'm going to move this down just a little bit. And then lastly, we now need to compute that nonlinear force vector. And in the first entry, we're going to have 1 over square root 2 times eta 1 plus 1 over square root 2 times eta 2. That quantity cubed times 0. And then all of this now is equal to 0, 0. Where this expression that I've circled, not without the cube though, that right there, that is what x1 is equal to when you do the modal expansion. Okay, so because these eigenvectors or these mode shapes have been mass orthonormalized, we're going to get out of here 1, or the identity matrix from there, from here. From the stiffness contribution, we're going to get the matrix 1, 0, 0, 3, where 1 and 3 are the natural frequencies squared. And then this last term right here, oops, not need to erase that. This gives us the following. We'll have the square root 2 over 4 times eta 1 cubed plus 3 square root 2 over 4 times the quantity eta 1 squared times eta 2 plus eta 1 times eta 2 squared plus the square root of 2 over 4 times eta 2 cubed and then 0. That's that vector. And so what we end up with is two equations, the first being eta 1 double dot plus eta 1 plus square root 2 over 4 times the quantity eta 1 cubed plus 3 eta 1 squared eta 2 plus 3 eta 1 eta 2 squared plus eta 2 cubed equal to 0. And then we get eta 1, eta 2 double dot plus 3 eta 2, and that is equal to 0. And we end up with mode coupling shown right here in green.
So all of those terms that I've, highlighted in green there, those are the ones that will allow these two modes to exchange energy. Okay. So these equations remain coupled under this linear modal transformation, which you might think that maybe we have the wrong transformation. That is something we'll come back to when we start nonlinear normal mode theory. Okay, any questions?
Yeah.
Okay.
So here we can see that the coupling is only on the first equation. So when an energy exchange happens, it's going to happen in one way or two ways?
A good question. So I don't know, actually. It's a good question. That's something we should investigate.
Well, so based off of his, it might be the same question, but is he asking like if there's a bucket of energy and the two frequencies don't necessarily have to have the same amount, but they just, take as much of the bucket as each one of them wants, or does one pass energy off to the other?
Sure. So let's start with just linear theories. The question is, how is, if there's a bucket of energy, how is it partitioned between the modes and then shared?
Yeah.
So if we start off with let's assume linear normal modes, then and you have a bucket of energy in the beginning, and then each mode comes by and scoops out their amount of energy, and then that's it. That's their energy for all time, assuming no damping. So there's no sharing, they can't talk to each other, nothing like that. So with this mode coupling, you can get different kinds of effects. When you have internal resonance conditions, you can get large sharing of energy. When you have not internal resonances, you can get kind of a small sharing of energy. When you have strong nonlinearity, which is kind of what we've looked at here, you can get all kinds of phenomena that happens between these modes. You can get cases where, and this is still kind of an open question as well, is what exactly does mode coupling mean? I mean, really we've used the wrong kind of transformation here. That's really the problem. And not to say that we even know what the right transformation exists or if one even exists. But, we've approached this decomposition here using linear normal modes, which don't even exist, is kind of where we're going. So it's a tough question to answer. What I can tell you is that, from what I've seen in my work, is that certainly in like transient effects, there is certainly mode coupling, but you get strong sharing when resonances happen, when these internal resonances occur. And that's what we're going to end up studying, is just resonance cases. Each system is unique, and you do need to just study it in general for the kinds of resonances that can occur, the kinds of phenomena that can occur as well. Now, the other question was, is the energy sharing one way or not? Maybe. I don't know. I mean, again, are we even using the right framework to address the problem? Right. That's kind of the real fundamental question here. So yeah, the key demonstration here is simply that if you try to use linear normal modes, you don't decouple equations. That's really what I'm trying to show here. What we're going to do now is consider similar sets of equations, but we're going to include damping, and we're going to include more nonlinear terms, basically. And then you can play with the parameters to determine what kind of nonlinearity you have. When I do like numerical examples, I've chosen to show where you have a nonlinear spring coupling the two masses together. But you could easily manipulate the parameters that I'll show in a moment. You could easily manipulate them to form this type of nonlinearity that's shown up here, and then study what happens there as well. That's not a bad idea for the homework, actually. In which case you would use the formulas we've already derived in class. You would just change the parameters to study that. Okay. And when we get to our data-driven portion, we will study this type of phenomena using like experimental measurements and using data-driven techniques to address what happens when you have just, a time series rather than a set of equations. Yeah.
The other question I had was, how did you find phi 1 and phi 2? Is that something we learned like that linear vibrations class? Like I could go look in a book and that would.
So, yeah, that's one of the underlying assumptions we have, but I can give you some YouTube videos to watch. Yeah, so the way I did it, I just used MATLAB to calculate them, to be honest. But you can calculate these by hand as well. I mean,
So about the T.
yeah, these guys right here.
So I've been doing this, a lot of this. So basically what you're going to do, you need to find first the equilibrium points.
Yep.
And you need to linearize around this equilibrium point. Then you're going to add an eigenvalues and the eigenvectors. So these are basically just the eigenvectors around that equilibrium point. And I think the only equilibrium point that works here, I think, is the 0, 0.
Yep.
So this is why you only have these.
Yep.
If you have a different equilibrium point and you linearize around the different equilibrium points, you're going to have different ones.
Yeah, absolutely. Yeah, we have made the assumption. Yeah, we're studying a simple system here.
Yeah.
So you're right. There's only 0, 0, 1 equilibrium point in this system. And yeah, we simply skipped from there to there. Yeah. And Mikey, this is something that you did learn from me in the past.
Yeah, it's just.
But it's been years, I get
It's
it.
a long, everything's been a fire hose. So.
Right, I get it. This class in general is very dense. This topic is very dense. Yeah, I mean, if you're wondering, it takes me like 4 to 6 hours to make one of these. It is long, yeah. So you're not the only one feeling the pain. I mean, this is very interesting, but it is, for me, it's a lot of work. It's very time consuming. Okay. It's so time consuming that I've actually not erased some of the equations, for example, because they are just abysmally long. Okay, but let's assume that you've done some type of modal decomposition, which doesn't really decompose them. But now we're studying in a modal domain rather than a spatial domain, meaning that we're studying etas, except that we're going to use u's. We're going to use u's instead of etas. All right, so we're going to consider two modes. The first one being u1, and so this equation is going to be u1 double dot plus omega 1 squared u1, and this is going to be equal to minus 2 c1 times eta times u1 dot, that's our weak damping for this mode, plus eta times the quantity alpha 1 u1 cubed plus alpha 2 u1 squared u2 plus alpha 3 u1 u2 squared plus alpha 4 u2 cubed is equal to 0. So you can already see how we have a similar form to what we just had before, where now we have alphas and they've absorbed a negative sign as well. All right, for our second equation, we're going to have u2 double dot plus omega 2 squared u2 is equal to minus 2 times c2 epsilon u2 dot plus epsilon times alpha 5 u1 cubed plus alpha 6 u1 squared u2 plus alpha 7 times u1 u2 squared plus alpha 8 times u2 cubed. That's equal to 0. So in the case that we just saw before, alpha 5, alpha 6, alpha 7, alpha 8 were all equal to 0. And the other alphas were equal to whatever parameters were above. Okay, so from here, we're going to apply the method of multiple scales. We're going to say that ui is equal to ui 0, which is a function of t0 and t1, plus epsilon ui times ui 1, function of t0, t1, plus epsilon squared ui 2, function of t0, t1, plus so on. And here I is equal to 1, 2. So we're expanding both of the modes here into their own series. We then plug that in along with the derivatives into the equations of motions, collect by orders of epsilon, set each order of epsilon equal to 0, and then that results in the following. We'll get d0 squared times u1 0. So this is the 0th term of the first mode u1 plus omega 1 squared u1 0 is equal to 0. And then our second equation, we will get d0 squared u2 0, which is now the 0th term of the second mode u2 plus omega 2 squared times u2 0 equal to 0. We can go ahead and solve these equations. We'll get for u1 0, this is equal to a1, which is just a function of t1 times e to the j omega 1 t0 plus the complex conjugate. And then u2 0 is equal to big A2 function of t1 times e to the j omega 2 t0 plus its complex conjugate. Okay, we're then going to take the solution for the u1 0, u2 0. We're going to plug that in at order epsilon to the first this time. And I see some people writing, so I'll let you guys finish because the next equation is going to take up the whole screen. Which is why I didn't erase it, because it would have been here for like 10 minutes. Okay, so when we substitute in order 1, you get a lot of terms shown here. I'm going to go ahead and circle certain terms. So first off, right here, this term, right here that I'm circling in blue, this is our obvious secular term. Meaning if there's no resonance or internal resonance or anything interesting going on, or subharmonics or primary or anything like that, then this is the only one we care about. And we also want to look at other potentially secular terms. The first one is right here that I'm going to circle in orange. So this is a potentially secular term. There's another one down here. Green. And then there's one more right here that I'm going to circle in purple.
Could you please say again how do you identify the potential signal?
Yeah, I'm about to go through that actually. Well, I'm not going to say that exactly, but what I say will hopefully address that. So I'll just try to say both. Okay, so we're looking for terms that could potentially have a e to the j omega 1 t0 term, something that's forcing at the natural frequency of this mode. So this first orange term here, we have e to the j omega 2 t0. So if omega 2 is equal to omega 1, which we've already assumed is not the case, but let's imagine that it is, then that's when it becomes a secular term. That would be known as a one-to-one internal resonance. So this guy leads to this one-to-one internal resonance, which I'm just going to write as IR. Okay, and then you would need to incorporate it into those along with the obvious secular terms. If we take a look at this green one, what we have here is omega 2 minus 2 omega 1. So in this case, if omega 2 is equal to, right, exactly, 1, which in this case you could call like a 1 to 3 internal resonance. Based on the way I've put omega 2 first. If you put omega 1 first, then you switch these ratios. So if that's the case, then you get resonance there. In this purple case, we have omega 1 minus omega 2 times omega 2. So if you had, let's say, omega 1 is approximately 3 omega 2, or, if we build based on that, that would be like a 3-to-1 internal resonance. That would be possible. Now, we've assumed that the modes are distinct and ordered properly such that this one can't occur and neither can that one. So neither the orange or the purple ones can be secular based on the assumptions we made on the natural frequencies, that they're distinct, so we can't have 1-to-1 because they're not the same frequency, and that omega 1 is less than omega 2. And so therefore omega 1 can't be equal to 2 times omega 2, or 3 times omega 2. However, omega 2 is larger than omega 1 and could potentially be 3 times omega 1. Okay, let's just briefly circle the obvious secular terms in the second equation because they also show up, and then the potentially secular terms. So in blue here, this is, again, the obvious ones. In orange will be our one-to-one potentially secular term. Green as well, we get this alpha 6 term. And then one more term. Okay. All right, we just had this discussion. So first, we can have omega 2 approximately equal to omega 1. This gives us that 1-to-1 internal resonance. We can also have omega 2 is approximately equal to 3 omega 1. Again, this is our 1-to-3 internal resonance. And then we can have that omega 2 is approximately omega 1/3. Which we would say is that 3-to-1 internal resonance. And we are only going to consider the second case. Yeah. Not to say that you couldn't study the other cases, you could. We're just going to consider this middle case.
So if we were dealing with, like a second order nonlinearity, it would be a 1-to-1, 1-to-2, and 2-to-1?
Yep. And if you had like a quintic, you would have 5-to-1s and so forth. Yeah, so like I said, we're only going to study this one case, and you can apply the same kind of analysis to the rest of the cases, quite simply. With that, we are out of time, so we'll stop here. In the next class, next week, we will go through the analysis of studying this. We'll study steady state responses, and then we'll look at some of the amplitudes and how the modes exchange energy.